Hi, everyone. My name is Danielle Heymann, and I'm a data scientist at the Applied Intelligence Discovery Lab that's part of Accenture Federal Services. And today I'm going to be presenting on methods in constrained community detection and optimization. Hi, everyone. My name is Danielle Heymann. I'm a data scientist at the Applied Intelligence Discovery Lab that's part of Accenture Federal Services. And today I'm going to be presenting our work on methods in constrained community detection, an integer optimization model, and heuristic approach for cohort creation. So we'll go through an introduction, a bit about the methodology that we developed. We'll go through the integer program model, the constrained community detection heuristic, comparison of methods, and a discussion after. So to begin, as we've seen so far, the COVID pandemic has brought a lot of organizations and schools to a virtual environment. And more recently, we're seeing that as vaccines and even boosters now have become more readily available, many organizations and educational institutions are starting to make the shift from a virtual environment to physical office spaces in schools. Now, this presents a problem in some cases because you have still a potential spread of the virus. So what we're trying to address here is how do we reduce that spread, and by using a constrained community detection heuristic or an integer program, we're able to address reducing the newly created links in a contact network. So we developed these two methods to address safety and caution with respect to containment of COVID-19 during the shift from a virtual environment to physical setting. And we have both an IP formulation and a constrained community detection heuristic that aims for the same objective. So to address this objective, we start with an initial contact matrix, and what we're trying to accomplish is reduce the amount of extra edges that are introduced when we make cohorts. So if you look at the graph to the left, and this is after applying the teacher program and getting a solution for how to partition the set, that graph is the initial contact matrix. So ideally, in the created cohorts, we don't want to create extra edges that are not in this initial contact matrix. And what this means is contact matrix, this could represent, in the context of COVID-19, a large group of individuals or an organization who are looking to move back to the office, and that contact matrix really represents who is regularly in contact with who else in that organization during, it could be the last month or the last week, whatever kind of survey or method the organization wants to implement. And also to add, this formulation can be generalized to other applications from constrained community detection, because this is something that there are algorithms for community detection and constrained community detection, but this specific formulation handles a minimum and maximum capacity constraint, which hasn't been seen much in research. So that's why we developed our own methodology here. So our first approach was to develop an integer programming optimization model, and this would give us, an optimal solution. And we have two formulations for this approach because we wanted to see, we came up with two formulations, and it was interesting to look at how their performance compared in whether the graph was sparse or dense. So the first formulation is based on the incidence function mapping of a graph, and we model it after that. The second formulation is based on correlation clustering, which we take into account dissociation and association. And this is developed in Python. We did use the Gurobi solver, very, very powerful solver. It is time consuming with the IP, but it's a very good diagnostic measure that we use to analyze the accuracy of the heuristic. And moving on to the heuristic, again, it aims to solve the same constrained community detection problem. We developed it in R, it's all open source, and it takes on an iterative approach and still keeps those capacity constraints and cohort number constraints intact. To note, it's significantly quicker than the IP optimization model, and we'll get to that towards the end where we can compare the methods. But as it's an approximation heuristic, it does not always achieve optimality and can get stuck in local mins. So there's a trade-off. So we'll dive into the integer programming formulation. Both of the models have the same input variables and parameters. They're designed in a similar manner there. So as mentioned before, that the graph that we have as input is a contact network of individuals who work in the same office, or it could be students in the same classes at school. Test graphs for this case are generated with Heuristic random graphs. And for the parameters, we have total cohorts, which is the user-defined number of cohorts, which the set of individuals in the contact network will be partitioned to. We have the minimum cohort size, the maximum cohort size, the adjacency matrix of our graph G. So if we have Aij is 1, that would indicate that an edge exists between two vertices in that graph, and otherwise it's 0, they're not adjacent. Cost matrix, on the other hand, is the complement. So we formulate in this way because any extra edges that are introduced into those solution cohorts, which are essentially complete graphs, because we assume that the individuals are all in contact with each other, those extra edges will incur a cost. So that's why we have, if they're not adjacent, then we have the cost matrix 1 for that set. And then otherwise the cost matrix is 0. So if two vertices are adjacent in the contact network. So now we're going to move on to our first formulation, and this formulation is based on really the definition of incidence function mapping. So with an integer program, mixed integer program, we need linear constraints and an objective. So that's what kind of drove this style of a model. And we designed this so that we have a relationship between the nodes and the edges, and the constraints force those relationships. But this is a little illustration of how the model is designed. So the y variables are representing the nodes, where the X variables represent the edges, and then there's a third index to represent the cohort. And we'll get more in depth with this really soon. So next we will discuss the decision variables. So N is a set of nodes that represents the individuals in the network, where C is a set of cohorts, and this X variable is a binary variable determining if there exists an edge in the solution between person P, teammate T, and cohort C, where Y is a binary variable that can be seen as like an assignment variable. So if person P is in cohort C. In our objective function, we are looking to minimize cost, and that cost is associated with introducing new edges, which would represent in-person interactions that did not exist in the initial contact matrix. For comparison purposes, we're just looking at the lower triangular matrix. So we have this here because we don't want to double count the penalties. And in the next formulation, we don't need to do that. So this just keeps it consistent. First constraint for this formulation is unique assignment. So an individual can only be sent to one cohort. You have your binary integer constraints. This is where it's a bit more interesting. So these constraints are forcing that relationship between the nodes and edges. So again, if we think of X as an edge between two individuals and Y as the nodes, these are two upper bounding and lower bounding constraints that would either, the upper bound constraint would force X to 0 unless both Y PC and Y TC of that X PTC have values of 1. And this lower bound constraint forces X PTC to 1 if both Y PC and Y TC have values of 1. So we have the lower and upper bound constraints that really make this relationship happen, and we're able to model the problem like a graph. And these are pretty straightforward, just our minimum and maximum cohort size constraints. And again, the user can define these. Next, we'll go on to the formulation for the correlation clustering version of the IP. So again, we have two formulations just for analysis and to understand if what we're trying to do, why we have these IPs are for a diagnostic measure. So they do take a while to solve, and it's worth having two versions to see if one can get to the objective, to the optimal solution quicker than the other, because they handle sparse and dense graphs differently. The correlation clustering formulation establishes relationships between cohorts and individuals by enforcing the dissociation and the association of these entities through the model constraints. So again, we have N as a set of nodes, C is a set of cohorts. Now this Zij variable, notice it's we just have two indices for this. This will indicate either dissociation where I and J, well, it just indicates dissociation where I and J can refer to either cohorts or individuals in the network. And it's 1 if I and j are in different clusters, and 0 otherwise. So 1 for dissociation. Keep that in mind as we go through this. It's a neat way of showing this. So again, the objective function, we're minimizing the costs associated with introducing new edges, which would represent new in-person interactions, which we're trying to avoid with COVID-19. So same scoring method. Here we consider the entire matrix because the denominator is already preventing double counting the penalties. And on to our constraints. So again, we have this cohort unique assignment constraint, and again, Z is for dissociation if it's 1. So if it's associated, it would be 0, and we can only have one person to a cohort. So binary integer constraint, and these really deal with the correlation clustering. And the first one is the cohort dissociation identity constraint, and we created this to as an assumption that if you look at Zij, if I and j in the cohort are considered, it's assumed that each cohort must be dissociated with another cohort. You can't have those entities can't be grouped together. A cohort is separate from a cohort. Pair identity, so Zij equals Zji. If person A and person B are associated, then or dissociated, or then person B and person A have the same value. And this is the main correlation clustering constraint. So this constraint shows us, so if Zij takes on the value of 0, as we said, then I and j are associated. So if we look at any 3 entities, and again, it can be cohorts or people, the dissociation, which takes value of 1, of any 2 has to be greater than the association. So we set that up like this. It's a conditional kind of constraint there. And as before, we have the min and max cohort size constraints. And I think that's it for the formulations. So we set up some tests and ran them. An interesting note is that similarly with a lot of other optimization formulations, we do have multiple optimal solutions here. So depending on the context or the case, it could be nice for an organization to have a few different solutions for pairings, but just to note that that's normal and feasible. And here's a little example. Next, we're going to move on to the constrained community detection heuristic. So this is a little different than the IPs because with the constrained community detection heuristic, we actually have a feasible solution upon initialization. We set it up like that. Whereas with the IPs, because we the solver applies a relaxation to the integrality constraint when it solves and goes through, a series of branching bounds, cutting planes, other kind of pre-solving strategies. The first solution is not necessarily feasible for the IP. So it's a little different for this heuristic that we designed. Takes on an iterative approach with two main functions, so the switch and the transfer function, and they do exactly that. So a little overview. So we start with the cohort creation, initialize variables, execute the switch function. If the objective is improved, then we keep iterating through the switch function until it's not, until we've exhausted it. And then we go through the transfer function again, until exhaustively we're not improving the objective. And if you go through both of these steps exhaustively, so if the objective was not improved and there also wasn't at least one improvement from the switch function, then we are done at that point. But if you still, so you would have to exhaust this function and then exhaust this function to be done with the heuristic. If, for example, you go through an iteration of the switch function and it improves the objective by 1 point and it's exhausted, and then you execute the transfer function and nothing improves, you're still not finished and you have to go through the whole process again until there's absolutely no change in that first process and no change in the second process. Very exhaustive approach there. This is kind of a deeper dive into the switch function, and basically what we're doing in the switch function is swapping members of cohorts done in a very linear way. Use like linear sum assignment to try to identify what swap should take place, and this is iterative itself as well. So a little deeper dive there. That's all in the paper too, in the appendix for further reference. Okay. Transfer function, similar approach, but this time instead of just swapping two individuals, we are removing one individual and adding it to another group. So there are a lot of checks within this function to make sure that there's capacity in the group that it's going to, and to make sure that there is at least the min capacity plus one in a group that has a member leaving, because we are actively enforcing those minimum and maximum capacity constraints throughout every iteration. And you could stop this heuristic at any point and the solution will always be feasible. So that's one good thing or bad thing. And so the reason why the transfer function has to go after the switch function is because if we think about it, this transfer function does constrain the problem further by either adding an individual or removing an individual. The swapping doesn't add another constraint. So this helps get to a better local minimum. And we've tried switching the order and have found that experimentally as well. And here's a test example. So we have a variety of ergo-strength test graphs of different sizes and different probability of edge creation. And the heuristic performed pretty well. So to compare the methods, clearly we see that the heuristic is very fast compared to the IPs. There's a little bit of a trade-off. This is a minimization problem, so depending on the context of the problem, this can either be fine or not. It's pretty close in value to the optimal solution of the IPs, so that's very exciting, especially for the difference in time. So this was great to see. Some findings, so that sparser graphs resulted in a longer runtime, and that was for all the methods. As we saw, the heuristic is a lot quicker than the integer program models, and the trade-off between speed and optimality truly depends on the context and specific use case and the cost of such small changes in the objective value. For future work, we'd potentially improve the objective value by also implementing a pre-solve strategy that could include network flow algorithms like the Ford-Fulkerson algorithm, which in the Karate Club, they use that as well. We could also leverage K-trust networks throughout the heuristic during the iterative phase. And some references. And that's all. Thank you so much for watching. And definitely check out our paper in the conference proceedings.